Well, there's hope that NASA could regain control of the lost Voyager 2 probe after a heartbeat signal was picked up. Contact with the spacecraft, launched in 1977, was lost when a wrong command was sent, tilting its antenna 2 degrees away from Earth. NASA will attempt to regain control from Canberra this week, where a large dish will beam the correct command in the direction of the craft.
More than 13 billion miles from Earth, a spacecraft built in the 1970s is still moving through the darkness between the stars. Voyager 2 has always lived in the shadow of its twin. It followed a slower route and reached interstellar space years later. Yet that longer journey allowed it to do something no other spacecraft has repeated.
Currently, the furthest man-made objects from Earth are the Voyager space probes, launched in 1977. Voyager 2 is currently 17 billion kilometers from Earth. That's like going to Pluto and back, and then back to Pluto again, roughly. And we can still contact it. How? Let's find out.
It launched on August 20th, 1977, 16 days before Voyager 1. The numbering reflected which craft was expected to reach its main targets first, not the launch order. Voyager 1 took the faster path past Jupiter and Saturn. Voyager 2 used the gravity of one planet after another to continue toward Uranus and Neptune. That choice made it the only spacecraft in history to visit all 4 giant planets. By the time it reached interstellar space in 2018, it had already spent 4 decades rewriting planetary science. What it found there made it even more valuable.
And even back in the late 70s, we could see with the Voyager data that something curious was going on with Europa. And over the course of the past several decades, we've now come to learn and appreciate that the outer solar system has got a small fleet of ice-covered worlds.
The only visitor to Uranus and Neptune. Voyager 2 reached Jupiter in 1979 and Saturn in 1981, observing Io's volcanoes, Europa's fractured ice, and the complexity of Saturn's rings. Those encounters alone would have made it one of the most successful planetary missions ever attempted. But Voyager 2 kept going. During its 1986 Uranus flyby, Voyager 2 discovered 10 moons and 2 rings. It measured the planet's extreme tilt and found a magnetic field sharply offset from its rotation axis, a strange arrangement that still challenges theories of how planetary magnetic fields form. Because no spacecraft has returned since, much of what scientists know about Uranus at close range still comes from this single encounter. 3 years later, it reached Neptune. There, it discovered 6 moons, recorded winds of roughly 2,400 kilometers per hour, and examined Triton, Neptune's largest moon. Voyager 2 photographed nitrogen geysers erupting from Triton's frozen surface and gathered evidence that the moon was probably captured from the Kuiper Belt. After Neptune, its cameras were switched off, but other instruments remained active. The mission changed from photographing distant worlds to measuring particles, plasma, and magnetic fields that could not be seen directly. The spacecraft had completed its tour of the planets, but it had not completed its scientific journey. Voyager 2 was now heading toward the edge of the Sun's influence, crossing the Sun's final boundary. The Sun releases charged particles called the solar wind, creating a vast bubble around the solar system called the heliosphere. This bubble surrounds the planets and helps shield them from some of the high-energy material traveling through the galaxy. Its outer boundary is the heliopause. Beyond it lies the interstellar medium, a thin mixture of plasma, dust, and magnetic fields between stars. Voyager 2 crossed this boundary on November 5, 2018, more than 6 years after Voyager 1. The delay came from its longer planetary route, but it also gave scientists a second crossing in another direction and during a different stage of the solar cycle. Crucially, Voyager 2 arrived with a working plasma science instrument. That detector measured the temperature, density, and movement of charged particles directly. The equivalent instrument on Voyager 1 had failed in 1980, leaving its crossing to be reconstructed indirectly through readings from its other instruments. Voyager 2 could measure the plasma itself while moving from one environment into the other. For the first time, researchers obtained direct plasma readings on both sides of the heliopause during a crossing. 5 Nature Astronomy papers published in 2019 explain the findings. The boundary was not the clean dividing line many models had predicted. A border that refused to stay simple. Scientists had pictured the heliopause as a fairly sharp edge, where the solar wind stopped and interstellar space began. Voyager 2 revealed a more complicated transition. It detected compressed plasma, disturbed particles, and a boundary structure different from the one encountered by Voyager 1. The 2 spacecraft had crossed separate parts of a huge, changing border from different directions, showing that one measurement could never fully explain the heliopause. Another result was just as puzzling. Voyager 1 crossed the heliopause at about 121.6 astronomical units from the Sun. Voyager 2 crossed at roughly 119 astronomical units. The crossings happened 6 years apart under different levels of solar activity, yet their distances were surprisingly close. Models expected the heliosphere to expand and contract more dramatically as the strength of the solar wind changed. If the solar wind was not moving the boundary as predicted, what was controlling its position? The answer is still unclear. What interstellar space is really like? Voyager 2 also challenged the idea that the space between stars is simply empty. It is extremely thin, but it contains plasma, radiation, dust, and magnetic fields. Voyager 2 detected a sharp change between the hot, thin solar plasma and the denser plasma beyond the boundary. Measurements showed that interstellar plasma was far denser than the solar wind near the heliopause. Voyager 2 also provided a direct temperature reading. The plasma beyond the boundary was cooler than the material just inside it, though still thousands of degrees. In plasma physics, temperature reflects particle motion, so a thin cloud can be extremely hot without behaving like hot air on Earth. Even beyond the heliopause, the surrounding material was still affected by the heliosphere. The solar system's influence faded through a broad, active region. The heliosphere leaks. The most surprising discovery was that the heliopause was not sealed. Particles crossed it in both directions. Before Voyager 1 passed through the boundary, it detected signs of interstellar particles moving inward. Voyager 2 later found solar particles leaking outward from another region. Because the measurements came from different directions and times, the leakage appeared to be a property of the boundary itself. The heliopause is better imagined as a coastline than a wall. 2 environments meet, exchange material, and change depending on where they are measured. Voyager 2 revealed not simply where the solar system ended, but how the Sun interacts with the galaxy around it. Why every remaining year matters. Voyager 2 is now traveling through interstellar space in a different direction from its twin. Together, they provide two measurement points across an enormous region. Together, the probes help test competing ideas about the heliosphere's shape, from a long comet-like tail to a rounder structure shaped by magnetic forces. Voyager 2's remaining instruments measure magnetic fields and plasma waves, helping researchers track changes over time. Once the Voyagers stop transmitting, there will be no replacement nearby. No other active mission is collecting this kind of data beyond the heliopause. A future probe would take decades to design, launch, and reach the same distance. Every additional year matters because the spacecraft records a region. Humanity cannot currently reach another way. Its importance comes from continuity. A single measurement can capture an unusual moment, but decades of readings reveal patterns, changes, and events that no brief mission could separate. Each signal therefore adds another point to a scientific record that began near the giant planets and now continues beyond the protective reach of the Sun, with no replacement mission currently coming. A spacecraft running out of power. Voyager 2 receives electricity from 3 generators that convert heat from decaying plutonium-238 into power. At launch, the spacecraft produced about 470 watts. That supply has been falling ever since, decreasing by roughly 4 watts each year. 4 watts sounds small, but with almost no spare electricity, it can decide which instrument or heater survives. Engineers have disabled heaters and retired instruments to preserve the most valuable science. The plasma instrument that made the historic crossing measurements was switched off in 2024. Other instruments remain active, but the decline cannot be stopped. NASA must now redistribute the remaining electricity without triggering automatic safety systems. That is the purpose of a procedure engineers, nicknamed the Big Bang. The Big Bang Power Gamble. The Big Bang is not an explosion. It is a coordinated reconfiguration of several remaining power systems. Engineers plan to change several systems together, reducing the time Voyager spends in unstable intermediate states. Its fault protection software could otherwise detect an imbalance and begin shutting systems down. Voyager 2 is more than 16 light hours away, so engineers cannot react instantly. A command takes over 16 hours to arrive, and the response takes another 16 hours to return. Voyager 2 must execute the procedure alone. It is going first because it is slightly closer and better powered. Success could lead to a similar procedure on Voyager 1. The reward could be another year or more of scientific observations. The risk is placing a nearly 50-year-old machine into a fault state that may be difficult to reverse. The quiet twin goes first again. Voyager 2 has spent its mission doing what no other spacecraft could. Now it is being asked to go first again. A small JPL team operates hardware from another era, sending instructions across billions of miles and listening for a faint reply. Voyager 2 completed the picture, showing us worlds no other spacecraft has seen up close and measuring interstellar plasma directly. The Big Bang procedure is not simply an attempt to keep an old spacecraft alive. It is an effort to preserve one of humanity's only direct connections to interstellar space. For almost 50 years, Voyager 2 has kept going beyond every planned ending. Now its future may depend on one carefully prepared set of commands, traveling for 16 hours across the darkness toward a spacecraft that must face the outcome alone.